All right, let's do a couple more examples. Make sure that we really understand how to estimate the value of a limit both graphically and numerically by looking at a table of values. So on example 3, we have the limit as x approaches 0 of, what a strange looking function, x divided by the square root of x plus 1 minus 1. All right, so you might be looking at this thing going, why would I ever want to know what this function is doing? What a strange thing. How could this possibly ever come up? But it does. There's a very specific reason why we're doing something like this, but it's a secret reason I can't tell you yet until the next chapter. Oh, is the suspense killing you? It should be. All right, anyway. Oh, whoops, secret information here. Get rid of that real quick. Okay, anyway. So let's just look at this as a function. If we look at this as a function, if we were trying to stick 0 in here, it'd make a 0 on the top, which is okay as long as the bottom's not always also 0. But if I stick a 0 in the bottom, that one's 0. That's the square root of 1, which is 1. 1 minus 1 is 0. So it's that indeterminate form, 0 over 0, which we're going to see throughout the year as something very special. The graph could be approaching a particular number. We just don't know what it is. We want to know, hey, there's probably a hole here. What's the y value of that hole? So we're going to go over here to the graph screen. Well, actually, let's split screen this because who's going to remember that weird function? Nobody, not even me. All right, so y equals x divided by any parentheses around the bottom because there's no little fraction bar thingy, and square root x plus 1, arrow out of that thing, and then minus 1, and hit enter. All right, we've got the thing graphed. We'll go full screen, and that's weird. This function just looks like the graph just looks like a square root function. Okay, so what we want to do is attach ourselves to this graph and maybe trace it. I can trace that pretty easily here by just clicking on it and hovering around 0. So right exactly at 0. Maybe you can see it. It's like, oh, there it is. It was undefined for a second. But what are the y values approaching on either side? So it looks like it was approaching the number 2. Let me zoom in a little bit. Yeah, the graph looks like it's crossing through the grid marks at 2. And then I can trace it again and verify that, oh, it does look like that it's approaching 2 on either side. Let's get some more evidence, shall we, in the form of a table. All right, so I'm going to pull a table up here. Before we start putting the numbers in it, though, let's talk about how we actually build this table. Last time we were centered around the number 1. Here we're going to be centered around 0. So let's put a 0 right in the middle. This is where we're going to start. Okay, and then we're going to build our table a little bit bigger than 0 and a little bit smaller than 0. Anytime we do these limits, we want to see that it's approaching the same number on either side of our x value. So a little bit bigger than 0 would be 0.001. Then step away a little bit more, 0.01, and a little bit more, 0.1. And then keep it symmetric on the left side on the number line, smaller than 0. And since this is at the origin, this should be negative 0.001, negative 0.01, and negative 0.1. And then our calculator should find the value, the corresponding y values for each of those points. Let's see if it can handle it. All right, coming back over here, get rid of this 2. No, get rid of this 2. Keep the negative sign, 0.1, enter. And then how about a negative 0.01 and a negative 0.001. All right, and then it does look like that's approaching 2. I can put in the number 1 here. It should say undefined at that particular. Why 1? How about the number 0, which is what we're trying to evaluate? Okay, and then step away. We want to make sure it's the same number on either side. So 0.001, 0.01, and 0.1. And that does give me some nice evidence to suggest that the value of the limit there is 2. All right, so I will officially decree this as approximately 2. And we will, in the next lesson, be able to prove that it actually is 2 using some limit laws. All right, let's take a look at this next one here on example 4. On example 4, find the limit of f of x as x approaches 2, where x is f of x is equal to, we got a piecewise function, very strange one, 1 when x is not 2, but 0 when x is equal to 2. I'm going to graph this one by hand. Not that our graphing calculator can't handle it. As a matter of fact, it can, and I'll teach you how to do that in a separate video. But this one's so simple that we can just graph it by hand. All right, firstly, notice that this is essentially saying, this part right here, y is equal to 1, horizontal line, as long as x is not 2. So I'm going to draw myself a horizontal line at 1. We'll say that's 1. And then it is saying also, right here at 2, it's supposed to be 0. So it's an ordered pair, basically 2, 0. Right, so I'm going to count off to 2. Let's say that's 2 here. However, there should be a little tiny hole in my horizontal line, and should be able to put a little hole there, and maybe a oh, that looks fantastic. It's that whole googly eye situation, right? It fell off of my beautiful project, my poster board. It got glued to the seat someplace on the bus right there at 0. All right, so we can see that if we were to trace this function with a laser pointer, that the value of the function is always 1 on the left side of 2, and it's always 1 on the right side of 2. It's just that the function dips down right there at 0 at 2. It doesn't matter if it does. The rest of the function looks like the number 1 on either side. So I'm going to write this. I'm going to say that the limit as x approaches the number 2, right, of f of x. Like when you have a piecewise function, you don't want to put the piecewise function thing inside the limit, so we define it elsewhere, and then we just write the name of the function inside of the limit, and we can say that this thing is approximately equal to 1. Well, this one, I think there's probably enough evidence, since it's a constant function, to say that it was actually exactly equal to 1. But remember, we're just learning right now, at this very moment, how to approximate these, how to estimate them. All right, in the next little video, I will show you how to put piecewise functions like this in your graphing calculator, and perhaps something a little bit more complicated.